Hello and welcome to the A-Level Chemistry lecture series. In this video, we're going to start looking at chapter 19, section 3, and we're going to start getting into the actual nitty-gritty of the math and the cycles behind lattice energy, more specifically the Born-Haber or Hess cycles that we talked about in chapter 6 of last year. So let's get started. Born-Haber cycles for lattice energy are a bit more complex than the Born-Haber cycles we did in AS chemistry. And mainly, the reason for this is that they don't quite fit. There's too much information. We can determine the lattice energy, and as you can see here, we have the top portion of this Born-Haber cycle or Hess cycle, where we have the lattice energy. Remember, lattice energy is defined as the amount of energy that's released or absorbed when 1 mole of an ionic compound in the solid state is formed from the ions in the gaseous state. So this top line right here represents the lattice energy for the Born-Haber cycle or the Hess cycle. We have a label right there. We can determine this Hess cycle or this lattice energy by making a Hess cycle with elements in their standard state at the bottom. Now, we're going to need a few pieces of information in order to properly do this. The first is the enthalpy change of formation of the solid ionic compound. If we make a Hess cycle where the top is the lattice energy, if we put the elements in their standard state at the bottom, then when we look at this left side of the arrow, we're going from the elements in their standard state to ionic compound in the solid state. This is a definition that we learned last year. Whenever we're making any compound, doesn't need to be ionic, but it can be ionic. When we're making a compound from its elements in their standard states, that enthalpy change that we're looking at is the standard enthalpy change of formation. So the first piece of information we're going to need in order to complete this Hess cycle and do some mathematics with it is the standard enthalpy change of formation of whichever ionic compound we are making. Now, where this gets complicated is the other side of the equation. When we look at the left side of the Hess cycle, we're going from the elements in their standard states to ions in the gaseous states. We have not, either in A-level chemistry or in AS chemistry, ever discussed an enthalpy change of anything that goes from the elements in their standard states to the gaseous ion states. And that's because this right here, which we're going to label delta H1, is actually not just one enthalpy change. It is a combination of many enthalpy changes, which can include the enthalpy changes of atomization of the elements. It can include the enthalpy changes of ionization of the elements. And it can include the enthalpy changes of electron affinities of the elements. So for the different elements, we're going to have different things that come up here on this side because we can't go. It's not just one enthalpy change that relates going from the elements in the standard state to the gaseous ions. There's multiple parts to that process. Now, we're going to break down what this delta H1 is in a minute, but if we call this delta H1, I want you to focus on this equation right here. If we call this delta H1, because we have delta H lattice at the top, enthalpy change of formation on the right side, and notice it goes from the elements to the compound, because that's what formation is. And then delta H1 is going from the elements to the gaseous ions. Then if we do an alternate path arrow here, we can see that the enthalpy change of formation, let me get my pencil out. We can see that the enthalpy change of formation here is going to be equal to the enthalpy change number 1, which we have on this side, plus enthalpy change lattice, delta H lattice. Because remember, when we look at Hess cycles, when we do our alternate path arrow, we're going through the arrows that agree in direction, and then that's going to be equal to the arrow that disagrees. So delta HF is equal to delta H1 plus delta H lattice. If we rearrange this to isolate delta H lattice, we end up with delta H lattice is equal to delta HF minus delta H1, which is the equation we have right here. So we can actually find the enthalpy change of lattice of an ionic compound if we know its enthalpy change of formation and if we know all of the different enthalpy changes that make up the delta H1. So let's look at that delta H1 more closely, because we know it's going to be a combination of the atomization, ionization energies, and electron affinities of the elements that make up that ionic compound. But what exactly is the delta H1? What are the steps that it takes to go from the elements in the standard state to the gaseous ions? So looking at breaking that delta H1 down. So this is the exact same enthalpy change or Hess cycle diagram, but we're looking now specifically at lithium fluoride. So again, I have changed my ionic compound to lithium fluoride. So this on the right is the enthalpy change of formation of lithium fluoride, meaning that if we're looking at the elements in their elemental form that make up lithium fluoride, that's going to be solid lithium plus 1/2 F2 gas. Again, why 1/2? Because there's only one fluorine in lithium fluoride, and the enthalpy change of formation is defined as the creation of 1 mole of the solid compound, or the compound in its natural state. Enthalpy change lattice is at the top, because we are going from the ions in their gaseous state to the element in its solid state. So the compound in solid state. So we have lithium fluoride solid. What is that made out of? That's made out of lithium plus ions and F minus ions, both in the gas state. And then that leaves us with this left side, which is very complex, right? Why? The left side is not one enthalpy change, like as we said before. We call it delta H1, but there is no delta H1. Delta H1 is actually a combination of 4 different steps that grab the elements in their elemental form and turn them to the ions in the gas state. So what are these steps? Well, first of all, whenever we work with lattice energies and we look at this delta H1, we are working with 2 different elements. We're working here with the lithium and we're working with the fluorine. So when we look at the steps, they're actually going to be divided between the lithium and the fluorine. So let's start with the lithium. What does it take to grab this lithium in its solid state, because that is the natural state of lithium, and turn it all the way to lithium plus gas? 2 things need to happen here. First of all, the state of matter needs to change. The lithium needs to be turned from a solid to a gas. If you remember, that first step of turning the lithium from a solid to a gas is the enthalpy change of atomization. So the delta H of atomization of a metal, because you remember delta H of atomization is turning an element in its natural state to a gaseous atom, that is going to take care of turning this lithium solid to lithium gas. So out of the 4 steps, the very first step to go from this to this is to use the enthalpy change of atomization of the lithium to go from the solid lithium to the gaseous lithium. But that doesn't get us all the way there for this metal. It doesn't get us all the way there for that lithium. In order to go from this lithium gas now to the lithium plus gas, we need to do another step. We need to grab this lithium gas, and because it is gaining a positive charge, we're turning it to lithium plus gas. That means we're removing an electron from the lithium. And you can see that over here on this side, there's that electron. So we're going to remove an electron from that lithium. And in order to do that, we need the energy associated with removing an electron from an element. Well, if you remember from AICE chemistry from chapter 6, the amount of energy needed to remove an electron from an element is going to be its ionization energy. So this is going to be the delta H of ionization energy 1 of lithium. So step 1, turn the lithium from solid to gas by using the enthalpy change of atomization, because that's how much it takes to turn 1 mole of solid lithium, or the lithium in its elemental state, to 1 mole of gaseous atoms of lithium. The second step then is to turn the lithium from a gas to a lithium plus 1 gas, meaning to remove 1 electron, which will be the enthalpy change of ionization, the first enthalpy change of ionization of lithium. So that's the first 2 steps. The first 2 steps grab this metal, and this is always going to be the case with lattice energies, regardless whether it's lithium fluoride or magnesium chloride. We're going to grab the metal, use the atomization of that metal to turn into a gas atom, and then use its ionization energy to turn it into an ion. Now, depending on what that ion is, we could use multiple ionization energies in this process. Remember that the first ionization energy is when we remove 1 electron, when we make a plus 1 gas or ion. If we have something like magnesium, which has a plus 2 charge, so let me do this here in the side. So if we have something like magnesium with a plus 2 charge that needs a plus 2 charge, we would actually need to add a step, because magnesium will need to go from magnesium gas to magnesium plus 1 gas, removing an electron. That will be the enthalpy change of ionization energy, the first one of magnesium. And then we will need to turn the magnesium plus 1 gas to magnesium plus 2 gas by removing a second electron. And that will require a whole other step using the enthalpy change of ionization, but the second enthalpy change of ionization of magnesium. So because lithium is plus 1, we only need to do this 1. But if we needed a higher charge, plus 2, plus 3, we might need to do it multiple times. So that's the metal. The metal needs to be atomized first and then ionized by removing the electrons with ionization energy, either once, twice, 3 times, depending on the charge. On the other side of this, we have the nonmetal, in this case, fluorine. So fluorine here needs to go from 1/2 F2 gas all the way to F minus gas. So again, what is the first step? The first step with a nonmetal is going to be to atomize it. In step 3 here, we're turning that 1/2 F2 gas into just F gas. We're turning it into the atom of the element in the gas state. In order to do that, again, that is the enthalpy change of atomization. Because anytime we're going from an element in its elemental form to 1 mole of the atom of the gas, that's the enthalpy change of atomization. So step 3 here requires the enthalpy change of atomization of fluorine. So again, 2 different enthalpy changes of atomization. One of lithium down here, this one of fluorine to atomize it into its atom in the gas state. And then finally, we need to do a last 4th step. The 4th step here, once we have the fluorine gas, is to turn fluorine to its ionic form. But because it's an anion, to turn fluorine to that ionic form is not going to require us to remove an electron like it did with lithium. It's going to require us to add an electron into the fluorine. So we're not looking here at the enthalpy change of ionization, because we're creating not a metal cation, we're creating a non-metal anion, a negatively charged ion. So what is that enthalpy change? Well, we learned it in the last section. In order to add an electron and the amount of energy needed to add an electron, that's the enthalpy change of electron affinity. And this is going to be the first enthalpy change of electron affinity of fluorine, because we're only adding 1 electron to that fluorine atom. So notice that whole delta H1 that we had is not just 1 step, it's actually 4 different steps happening to 2 different elements. We first atomize and then we ionize. We atomize the lithium metal into a gas, and then we ionize it by removing an electron and turn it into a +1 ion. We atomize the fluorine by turning it into F gas from 1/2 F2 gas. We are breaking that bond that holds the molecule together. And then we are ionizing the fluorine by adding an electron in this case, because we have a non-metal. Again, if that non-metal was -2, we would need to do 2 electron affinities. If it was -3, we would need to do 3 electron affinities, so on and so forth. So that's the general steps, the general sequence that we see here. We're going to first atomize the metal, then use the ionization energy to ionize it into a cation of proper charge, however many electron ionization energies that takes. We're then going to atomize the nonmetal and then use the electron affinity of the nonmetal to turn it into the appropriately charged anion. Now, this is very complex, right? For a Hess cycle, this is a lot of steps. Normally, Hess cycles only include 3 enthalpy changes, not like we see in this case, 6 different enthalpy changes. So that's where Born-Haber cycles, or what we know as energy level diagrams, come in. Energy level diagrams are another way to represent a Born-Haber cycle. And you keep hearing me say this word. Born-Haber cycles are the same as Hess cycles that we talked about last year. So energy level diagrams are just another way of representing a Hess cycle. The diagram is still the same thing. It represents the pathways that we see. The difference with the energy level diagram is that now we have a vertical square diagram that is going to look at each individual step and whether that step is exothermic or endothermic. So, for example, looking at this, to compare it to that Hess cycle that we had before. In this Hess cycle, we have the ions, gaseous ions, turning into the ionic solid. That's the enthalpy change of lattice, or the lattice energy. We have the elements in elemental form turning into the solid and solid ionic compound. That's the enthalpy change of formation. And then we have the series of 4 steps that go from the elements to the gaseous ions that include atomization, ionization energy, and electron affinity. If we look at this, we actually still have all of those components. If we look here in yellow, oops, let me make that a little bigger. Here in yellow, we have the enthalpy change of the lattice. And that's still the same enthalpy change of the lattice that we saw earlier. It is now just pointing down instead of sideways. We're still going from the elements in their gaseous ions to the solid ionic compound. We still have the enthalpy change of formation here in pink. If we look at this arrow right here, we have the enthalpy change of formation. Why? We're going from the elements in their elemental forms, lithium solid plus 1/2 F2 gas, to the solid ionic compound. So we still have those 2 components. And then we still have delta H1. That delta H1 that we saw that was 4 different steps is still here. And we have it right here in blue. 1, 2, 3, 4 different steps. We're going from step number 1, which is right here. That was the atomization of the lithium. Step number 2 right here, that was the ionization of the lithium. Step number 3 right here, which is the atomization of the fluorine. And then step number 4, which was the ionization of the fluorine to F-. But why does it look so weird? Why isn't it a triangle? And why are some of the arrows pointing up, like these ones, while some of them point down, like this right here? One of the key differences in an energy level diagram is that it doesn't just show the steps, it actually shows whether each step is endothermic or exothermic. Endothermic processes or endothermic steps are represented with an arrow that points up. And that's because the system, the energy, the chemicals, are absorbing energy in those endothermic steps. So for example, here, that enthalpy change of atomization, and let me label that. That enthalpy change, delta HAT, That's too big. The delta HAT for the lithium is endothermic. It is positive. And we can see that because the arrow for that step points up. The enthalpy change of ionization energy, or actually let's redo this. Let's just call it IE1. So the ionization energy 1 for lithium, which we see here, going from lithium gas to lithium plus, is also endothermic. It is positive enthalpy change. That's why it points up. Here, the enthalpy change of atomization for fluorine, going from the fluorine gas to 1/2 F2 gas to the F gas, that's also endothermic. And you can see it points up. It is positive. But if we look at the other three, we can see here on the right that we have the enthalpy change of electron affinity 1, or we can just call it EA1. So we have the electron affinity 1 for fluorine, where it goes from F gas to F minus, and that is exothermic. It is negatively charged, and that's why that arrow now points down. So notice, this is that delta H1 right here. Atomization of lithium, ionization of lithium, atomization of fluorine, ionization of fluorine. But one of those three steps, the ionization of fluorine, the electron affinity is negative, and so that points down. Once we get to the lattice energy, we read this already. Lattice energy, delta H lattice, is always going to be negative. This delta H lattice for lithium fluoride, and let me actually put that here, lithium fluoride, is going to be exothermic. It's negative in value, in sign, and that's why it goes down. And then finally, the formation. Enthalpy change of formation of lithium fluoride is also exothermic. It is also negative, and that's why this arrow points out. Notice though, it also shows size or magnitude. Notice how the enthalpy change of formation of the lithium fluoride, that arrow is smaller than the enthalpy change of the lattice or lattice energy for the lithium fluoride, which is a much larger negative arrow. So we can tell just from looking at this energy level diagram whether the different steps are positive or negative, endothermic or exothermic, and which steps are more energetic than the others. So the number for the enthalpy, the lattice energy, is going to be much larger than the number for the formation of lithium fluoride. And we can visually see that with the arrow being bigger. So let's compare them side to side. This right here is the Hess cycle, or the Born-Haber cycle that we saw earlier, with all of the different steps for this Hess diagram. That the fact that the lattice energy plus the 4 different steps are equal to the enthalpy change of formation. Whereas here on this side, we have the energy level diagram. Exact same steps, and I'm going to highlight them here so you can see the comparison. Exact same steps. We have step number 1 here, going from that lithium solid plus 1/2 F2 gas to the lithium gas plus 1/2 F2 gas. That step is right here. Notice, same beginning, same end. Same beginning, same end. This one points up because it's endothermic. This one just points this way because that's how we're drawing it. Step number 2, going from the lithium gas plus 1/2 F2 gas to now the lithium plus 1/2 F2 gas plus the electron. Same exact step right here. We have the lithium gas and the fluorine gas, or we have the lithium plus 1, fluorine, and electron. Again, points up because it's endothermic. This one just points up because that's how we drew it. Step number 3. The change here being that the fluorine is being atomized. It goes from F2 gas, 1/2, to F gas. That's the same step number 3 right here. Exact same beginning, exact same end. Points up because it's endothermic. If we look at step 4, going from the fluorine gas to the fluorine minus gas. Step number 4 is right here as well. But notice, where this one points up, just because it's following that Hess cycle shape that we learned last year, this one points down because the delta H of electron affinity for fluorine is going to be negative in charge. And so we have an exothermic process, so it points down. Once we get up here, we have the enthalpy change, or lattice energy, or whatever you want to call it. We're going from the ions in the gas state to the solid ionic compound. Same thing right here. We have the step number 5, which is what we call it here, but it's still enthalpy lattice energy. But notice, we have it on both sides. This one points out because it's exothermic. This one points to the right because the Hess cycle for lattice energy has the lattice energy at the top, because that's what we're looking at. And then finally, we have, and I'm running out of colors, we have the enthalpy change of formation here. That's the same enthalpy change of formation we have here, going from the elements in the elemental form to the solid ionic compound. That's right here, going from the elements in the elemental form to this line, which represents the solid ionic compound. So it's the exact same thing. Now, how do we do the math for this? How do we visualize it? It's the same way. We have the alternate path arrow that we created here. The alternate path arrow still exists in the energy level diagram. It just has to start and end in the same place. So you'll notice here how the arrows create a path. We have this kind of loop where the arrows follow each other. And if we were to kind of go around in a circle, the only arrow that opposes that is this one right here. So this is going to be our arrow. This is our alternating path. Oops, let me make that smaller. This is our alternating path where all the arrows agree in direction. So what does that mean? Anything that's on the path of the arrow is added up. The arrow that is against the path is what it's equal to. So we have delta HF is equal to delta H, or we'll just call it here delta H1, the step 1, plus delta H2, step 2, plus delta H3, step 3, plus delta H4 for step 4, plus the lattice energy. Now we can condense all of this. All of these are what we called earlier delta H1. So we can condense this to just being delta HF is equal to delta H1 plus delta H lattice. Which means that delta H lattice is equal to delta HF minus delta H1, which is the same equation that we saw earlier in the PowerPoint when we were looking at just the Hess cycle. So let's try to draw one of these from scratch. Let's put everything that we just talked about together, everything we just learned together, and start from scratch. All right, so let's say that you're being asked, like you see here, to draw the energy level diagram for lattice energy of magnesium chloride and calculate delta H. Now, are you going to be asked to actually draw the energy level diagram all that often? It's not super common, but it does show up on the test sometimes. I will say maybe every 3 exams will have it on paper 4. So it is an important skill to learn. Now, step number 1, where you're trying to draw an energy level diagram for lattice energy specifically, is going to be to place your elements in their elemental form. Now, you do want to place this towards the bottom of your energy level diagram. One of the important skills or important things that you will learn as you do these is to start placing things appropriately. Because remember, if it's endothermic, we have to go up. If it's exothermic, we have to go down. So if you place this too high, you won't have enough place to go up. And if we place it too low, you won't have enough space for anything that is exothermic. So we're going to place our elements in their elemental form with a line on them towards the bottom of the energy level diagram, but not at the lowest level. In step 2, what we're going to do is we're going to start placing the different enthalpy changes. Remember, just like a Hess cycle, an energy level diagram is a combination of a number of enthalpy changes. So each arrow represents one enthalpy change. What is the first enthalpy change we want to put, which is the easiest to locate? Well, that's actually going to be an enthalpy change from AICE chemistry. And that enthalpy change is going to be the enthalpy change of formation. Because we're starting with the elements in their elemental form, if we put the ionic compound as a solid, what we will be creating here, if we connected it to an arrow, is the enthalpy change of formation. Because enthalpy change of formation is exothermic in this particular case, we will place that arrow facing down. You have to be careful. Some enthalpy change of formation are positive, some of them are going to be negative. So in this particular case, because it is exothermic, because it is negative, we draw the arrow facing down. This is going to represent the enthalpy change of formation of magnesium chloride, because we're going from the elements in the elemental form to the solid ionic compound, the solid magnesium chloride. Once we have this, what is the next thing we're going to place? Now that we have this, now that we have that one piece that is kind of counteractive to the rest of the energy, the level diagram, we are going to start to work on these elements and get them to a point where they're ions in their gaseous state. Remember, that delta H1 we saw earlier is the whole goal of delta H1 is to turn the elements in their elemental form into ions in the gas state. So what are we going to do here? The next thing we're going to place is we're going to pick one, and I usually recommend start with a metal, because then you'll see why in a second, it makes more sense. We're going to pick one of the two and start with enthalpy change of atomization. Now remember, enthalpy change of atomization will always, regardless what element you're working with, be positive. So we're going to place that arrow facing up, away from the enthalpy change of formation. So we're going to go up, and we're going to change that metal from Mg solid to Mg gas. We're going to atomize it, turn it into an atom in the gas state. That is going to be represented by the enthalpy change of atomization of magnesium solid. The next step, once we have that in the gas state, is going to work on that magnesium to make it into now an ion in the gas state, which is our ultimate goal. And so because we have a metal, because it is going to form a cation, a positive ion, we need to use the ionization energy. But you have to be careful here. We're going to ionize that metal. We're going to turn it into its positive ion. But you have to be cognizant, you have to be aware of what the charge of that metal is. In the case of magnesium, which is a group 2 metal, remember magnesium being a group 2 metal, because a group 2 metal, magnesium is going to turn into magnesium 2+. It has a 2+ ion. So we're actually not going to do one ionization here. We are going to do this ionization in 2 steps to get to +2. Ionization energy only removes 1 electron at a time. So what does that mean? We're going to do first the first ionization energy, which is going to be positive, and it's usually positive. We're going to do the first ionization energy for magnesium, but that's only going to turn magnesium to magnesium +1, not 2+. So we have to then do the ionization again, use the second ionization energy for magnesium to turn that magnesium from +1 to +2. So unlike the lithium we saw earlier, magnesium actually requires 2 ionization energies to get it to the proper charge. Because remember, when we're working with magnesium chloride, MgCl2, this is MgCl2 because magnesium is a 2+ charge when it's an ion. And then it's going to be made out of the chloride ion, which is Cl-. But we have a 1:2 ratio between magnesium and chlorine. So the 1 magnesium, we're going to ionize twice. Now, the next step, now that we have magnesium as a gas and an ion, which is what we wanted, we now have completely turned magnesium from the elemental form of magnesium to the gaseous ion. We can now work with chlorine. Notice that when we remove those electrons from magnesium, we're showing them, right? We remove one electron, we show that electron, E minus. We remove the second electron, we now have two electrons, 2 E minus. Now that we have done that to magnesium, we need to work on this chlorine. Chlorine is still in its elemental form, Cl2 gas. So what we're going to do next is we're going to grab that chlorine and we're going to give it the same treatment we gave magnesium. First, we're going to atomize the chlorine. So we're going to grab this chlorine, which is Cl2 gas, and we're going to turn that chlorine into 2 individual atoms of chlorine. Notice how for this, the chlorine does not change state of matter. State of matter is still a gas in both cases. But what changes, because remember, it's called atomization, what changes is that we're turning that chlorine from Cl2 to bonded chlorine atoms to 2 individual chlorine atoms, 2Cl, which is just a chlorine, really a free radical essentially, and another chlorine. So these are individual, they're separated from each other, not bonded together. So what does it take to do that? Well, it takes the atomization of chlorine, delta H atomization of Cl2. But you have to be careful. Atomization is defined, if you remember from section 2, as the creation of 1 mole of atoms of the element. In this particular case, we're not creating 1 mole of chlorine, we're creating 2 moles of atoms of chlorine, meaning that this delta HAT has to be multiplied by 2 because we're not creating 1 atom, we're creating 2 atoms or 2 moles of atoms. So this step right here is going to be 2 times the enthalpy change of atomization of chlorine. Now, one thing I will tell you about enthalpy changes, now that we know this many, you have to be careful because enthalpy changes can have multiple names. For example, here we have 2 times the atomization of chlorine, delta H atomization of chlorine. There's actually another name that we could give this procedure. Because we are essentially, all we're doing, when we go from Cl2 gas to 2Cl gas, all we're doing here is breaking that chlorine-chlorine bond. We're breaking 1 mole of chlorine-chlorine bonds. So this 2 times delta H of atomization is also equal to the bond energy of the chlorine-chlorine single bond. Because we're in the gas state already, we're breaking the bond. So whether we call this the enthalpy change of atomization of chlorine times 2, or we call it the bond energy of chlorine, and this will actually be a D, not an E. Oops. Or we call it the bond energy of chlorine, it's the same thing. The bond energy of chlorine will mean to break a chlorine-chlorine bond in the gas state, which is what we're doing to create 2 chlorine atoms in the gas state. The enthalpy change of atomization of chlorine times 2 would be to grab chlorine in its elemental form and create 2 moles of chlorine atoms in the gas state. Either way, we're doing the exact same thing. These numbers are equal to each other. So be careful. If you're ever doing one of these problems and you can't find an enthalpy change, think about what that enthalpy change is and think about, can I call it something else? If I have 2 delta H atomization for chlorine, but that's not given to me, what else could I call this? Oh, I can call it the bond energy for the chlorine-chlorine bond. And that might be given to you. You have to be aware that some of these enthalpy changes can be switched around. They're essentially the same thing. So now we got into the highest point in our energy level diagram. We've now gone from our elemental form up to the metal ion in the gas state and 2 chlorine atoms or non-metal atoms in the gas state. What is the last step? Remember, the goal of delta H1, which is what we're working on right now, is to go from the elements in their elemental form all the way to the ions in the gas state. Well, chlorine is not an ion yet. So what is the last thing we need to do? We need to grab that chlorine and turn it into an ion. Well, here's where this starts to go down. Why? The electron affinity for chlorine is actually negative. It's exothermic. Chlorine releases energy when electrons are added to it, when one electron is added to it. So that last part of delta H1 is actually going to be an exothermic process. We're going to grab these two chlorines, we're going to add an electron into each one to turn them into 2Cl minus in the gas state. Now you do got to be careful. The electron affinity of chlorine, the first electron affinity, is the addition of 1 mole of electrons to 1 mole of chlorine. Well, here we're adding 2 moles of electrons to 2 moles of chlorine. So this process to change the 2Cl gas plus 2 electrons to 2Cl minus gas is actually 2 times the electron affinity 1. Not the electron affinity 1 plus the electron affinity 2. We're not adding 2 electrons to the same chlorine. We're simply adding 2 moles of electrons to 2 moles of chlorine atoms. So we need to multiply the electron affinity times 2. That right there completes the delta H1 we're looking at. Those are the 4 steps. 1, 2, 3. 1, 2, because remember this was 1 step that happens twice. 1, 2, 3, 4 steps right there. Now the last step that we need to put on here that we still are not showing is the lattice energy itself. Remember, the definition of lattice energy is going from the gaseous ions, which we now have, to the solid ionic compound. We're going to finish the diagram by not drawing anything new. We're just connecting the ions in their gaseous state to the solid ionic compound. And delta H lattice, as we saw earlier in section 1, is always going to be exothermic. It's always going to be negative, pointing down. So make sure that you're showing that in your diagram. This is pointing down. And now we have our completed energy level diagram. We have the enthalpy change of formation, just like we had in the Hess cycle. We have the enthalpy change, the lattice energy, like we had in the Hess cycle. And we have that delta H1 going around here that we had in the Hess cycle as 4 different steps. Now, to calculate delta H lattice, we simply add up all of the enthalpy changes found in the alternate path. So essentially, if the lattice energy is going from the gaseous ions to the solid, then we can do this in 2 different ways. The first is to start where the lattice energy starts and go towards the ending magnesium chloride solid without crossing lattice energy. That's what this alternate path arrow does. It starts where lattice energy starts, it ends where lattice energy ends, but it does it through an alternate path. So in this particular case, we would be doing delta H lattice is equal to this is going up, this is going down. So these are going to be opposites, meaning that's going to be a negative. So it's going to be equal to, actually, I don't know why I'm writing this. It's on the next slide. So that's going to be equal to, the delta H lattice is going to be equal to the negative of the 2 times EA1. And again, why negative? And this is very important for you to look at. This is going to be negative because this arrow points down while this one points up. They don't agree in direction. Because they don't agree with direction, we are going to, because this one goes down, whereas the alternate path goes up, that is going to end up with a negative in front of it, which is that negative right here, negative 2x EA1. Then once we go on the other side, again, same thing. All of these arrows are pointing up while this one is pointing down. Because they're opposites, we are going to call this a negative sign. So it's going to be negative 2x delta HAT for chlorine, negative I1 and I2, so negative I1 and 2 for magnesium, negative delta HAT for magnesium. And then finally here, down here, this arrow is going down, this arrow is also going down, and so because they agree, that one's going to be positive. So delta HF is going to be positive. That's one way to do it. You can also use the mathematical way we learned earlier. If we learn you the mathematical way, we're going to have to draw a different alternate path arrow. So we're going to ignore the green one right here. And instead, we're going to draw an alternate path arrow that starts at our elements in their elemental form, and they follow the natural arrows. So all of these arrows agree in direction. So they all go together. This arrow being the only one that kind of disagrees, because if I continue this will have to be going up. This arrow disagrees, so that one's going to be separate. So what do we do here? Well, delta HF, because it's the one that disagrees, will be by itself. So it's going to be delta HF of MgCl2 is going to be equal to all of these added together. So delta HAT of magnesium plus the ionizations, so plus IE1 plus IE2 plus 2 times delta HAT for chlorine, which we have right here, plus 2 times EA, 2 times EA, 1, plus delta H lattice. And you might be saying, well, that's a different equation than this. Well, not really. Because if we isolate delta H lattice right here, which is what this equation did, all we have to do is now subtract all of this right here from delta HF. Meaning delta HF is going to be positive, all of these are going to be negative. If we look at them here, delta H positive, delta HF positive, delta H atomizations, both of them are negative. The ionization energies are negative. And the enthalpy change of atomization is negative. Or sorry, the electron affinity is negative. Again, because we're going to now subtract all of these from delta HF in the math, we end up with the same equation. So it doesn't matter whether you do the green arrow or the blue arrow, they're just two alternate ways of doing the exact same thing. So we shrunk this down now here. We have it a little smaller. We have the equation that we came up with, whichever way you do it. Once we have this, all we have to do is rearrange it to find what we want. And I like to put my positives first and my negatives second. So this is the exact same equation. We have delta H lat is equal to delta HF, which is going to be positive. That's why I put in the front. And then I have all my negatives. Well, all we're going to do is put all of those together and remove the negative sign. Oh, look at this. This is looking familiar. Going back to the earlier conversation, we have delta H lat is equal to delta H of formation minus all of this, which was what made up delta H1. So delta H lat is equal to delta H of formation minus delta H1, which is made up of all of these steps. We end up with the exact same equation that we saw in the first few slides of this section. All right. So the equation will serve you, but it's important for you to understand why the equation works. And more importantly, you need this because you need to be able to figure out what delta H is, delta H1 is. Delta H1 will be different from one compound to the next. So once we rearrange it, all we have to do, and again here, notice that the equation is the same. We plug in the numbers. So I have gone and gotten these. You would normally be given these during an exam. So I plug in the numbers for the enthalpy change of formation of magnesium chloride, the first electron affinity of chlorine, the atomization of chlorine, the first and second ionization energies of magnesium, and the magnesium atomization. And then you just do the math. You do the math, plug it in, and you end up with delta H lat is equal to negative 2,523 kilojoules per mole. Now you might be looking at me and saying, wow, that's a lot of work for one equation that I can just memorize. Yeah, it is, but the important thing about energy level diagrams, again, like I said, you're not asked to draw them every year, but the important thing is that you understand how to draw them, because the how to draw them, the understanding what these energy level diagrams are going to help you figure out what the delta H1 is. It's no longer an equation that you can just memorize, because the delta H1 is going to always be made out of electron affinities, atomization energies, and ionization energies. But depending on the compound you're doing, you might be using one, two, or all three of the ionization energies. The atomization might have to be multiplied, like we was with chlorine here. You might be using multiple electron affinities or multiplying the first electron affinity of the element. And all of that you won't really be able to tell unless you understand how the energy level diagram is figured out. All right? So let's keep going. So something you gotta be aware of is that it's not always gonna be this straightforward, right? Sometimes energy level diagrams can be used for things that are not lattice energy, or they can be used for other types of lattice energy problems where you might not use every single one of the same enthalpy changes that we just saw. So you gotta be careful. This kind of work, these kind of problems require a lot of critical thinking. Some of these can be very high level AO2 problems. So the following question is an example of this, and let's walk through it together. So the question says, the equation for the formation of gaseous sulfate ion is shown. And they give us the equation for the formation, delta HF, of the sulfate ion, SO42 minus gas. Solid sulfur plus 2O2 gas plus electrons, 2 electrons, yields SO42 minus gas. Calculate the standard enthalpy change of formation, delta HF, of the sulfate ion. It may be helpful to draw a labeled energy cycle. Use relevant data from table 1.1 in your calculations. So and then they give us a table. They give us a bunch of information. So before we tackle this problem, because this problem can be extremely difficult if you don't know what you're doing, if you can think critically, let's look at a few things. Number one, when we read the question says, it may be helpful to draw a labeled energy cycle. Notice that they don't tell you you have to, right? It may be helpful means that it is not part of the actual mark scheme. It's not part of the actual marks or points they give you. But sincerely speaking, this is a really, really hard problem to do without actually drawing your energy level cycle or energy level diagram. The other thing that you want to be aware of is that when we do these problems, they happens with a bunch of enthalpy problems, they give us this table filled with enthalpy changes. And a common mistake people make is that you see this and you're like, okay, I have to use all of them. Not necessarily. You might not need to use every single one of these enthalpy changes. You may end up using all of them. You may not. Do not fall in the trap of I have to use them. Because if you don't, which it happens fairly often, you're going to be doing work that is essentially going to just cancel out everything you work for. Don't fall in the trap of they give it to me so I have to use it. That is not an appropriate line of thought. Look at it, look at your energy level diagram, and if you need to use them, and if you don't, you don't. So let's actually tackle this problem now. Now I'm going to switch over to a different program. So let's look at the problem. I have the exact same problem here with all of my energy level diagrams. Now, I'm going to walk you through how to do this problem, or how I would do this problem if it was me taking this test. If I was sitting in the A-level exam and this problem came up, this is how I would tackle it. First of all, I will read this, and I will read that the equation for the formation of the gaseous sulfate ion is shown, and they give me an equation. Right away, I will go in here, and I will highlight that equation. Or you don't have highlighters in the A-level exam, but underline. Why are you going to underline this? This is what you're looking for. At the end of the day, you're drawing a diagram in the hopes that at some point in the diagram, you'll have this particular equation. Now it says, calculate the standard enthalpy change for formation. So calculate the enthalpy change for that. It may be helpful to draw an energy cycle, so I'm going to do that. Use the relevant calculations in the table. So I look at these calculations, and I have some that I recognize, some that I don't. Here I have lattice energy for barium sulfate. So this is delta H lat. I have the standard enthalpy change of formation of barium sulfate. So this is delta H F for barium sulfate. I'm going to underline the barium sulfate. I have standard enthalpy change of atomization for barium. So I have delta H atomization for barium. The first ionization energy for our barium, so IE1 and IE2 for barium. So first and second. Atomization of sulfur, so I have delta HAT for sulfur. I have the standard enthalpy change for the, this is the electron affinity 1 plus 2 for sulfur. So notice, what do I say? 1 plus 2, you're going from 0 to a negative 2. Also, I'm looking at and standard enthalpy change of electron affinity as well, but for oxygen going from 0 to 2. So this is also EA1 and EA2, but this is for oxygen. And then the bond energy, or D of OO. So this is everything I have. Now, that's a lot of symbols. And it's good to know which symbols go along with which of these enthalpy cycles, so we can kind of look at them at a glance and know what we're looking at. But when I draw my energy level diagram, you'll notice I'll do something else. And just watch what I do when I draw this diagram as far as labeling the enthalpy changes. So what I'm going to do here is I'm going to essentially take what I know, right? I know how to do lattice energy. So I'm going to start there and kind of look around to see where this equation will fit into my energy level diagram. I'm not going to try to build one out of this because this is a lot of different enthalpy changes, some of which we haven't used before, right? Like we haven't used 3 different elements. We just done binary, just single element compounds or 2 element compounds. So I'm just going to start with where I would normally start with lattice energy and then hope that in some of that I will end up with what I need. So I'm going to start with my elements in their elemental form, like I would with any energy level diagram for lattice energy. And I am giving lattice energy, so I know it has to be something similar. So I'm going to start with a line that is very crooked. Let's try that again. So I'm going to start with my line. And in this line, I'm going to put the elements that form barium sulfate. Because notice that here we have the sulfur, we have the oxygen, but we don't have the barium. The idea here is that if we're working barium sulfate, the elements that make up barium sulfate are barium, Ba, solid, 1 barium, 1 sulfur, so plus S, solid, plus oxygen. The better 4 oxygens. The elemental form of oxygen is O2 gas. But because I need 4 oxygens in barium sulfate, I'm going to say 2 O2 gas. So those are my elements in their elemental form. Well, the next step in drawing an energy level diagram for lattice energy will be to write an arrow pointing down and put the actual solid compound here. So that will be BaSO4, barium sulfate, as a solid. Now, normally we will label this with delta H of formation of barium sulfate. But look at what I'm going to do in order to make my life easier. Because remember, time is of the essence when you're doing this test. Instead of writing delta H formation BaSO4 solid, which is a handful, I already have that labeled up here, right? I have the enthalpy change of formation of barium sulfate right here. That's what this second line is. So I'm going to call this A, and I'm just going to label this A. Because remember, this diagram is not being graded. So why am I going to bother doing all neat labels very accurately drawn if I'm not being graded on it? So I'm just going to make this A right here. And now I'm going to label this A. So now I know that this section right here is the enthalpy change of formation of barium sulfate. Once I have that, I'm going to go and I'm going to follow all my steps. So we're going to start with the metal, with the barium. When we have that barium, we're going to first atomize it. That's what we learned earlier. So I'm going to grab the barium and I'm going to put Ba gas, because I'm atomizing the barium. And that's going to be the enthalpy change of atomization of barium, which we have right here. So again, I'm not going to label this with delta H, AT, Ba. I'm going to just put B. And then I'm going to go over to my chart. I'm going to label this B. Now, I still need to put all of these other things. So I'm going to put plus S solid plus 2O2 gas. I don't worry about it being too neat. Next, I'm going to then ionize the barium. Now, if you remember, because sulfate is 2-, barium being a group 2 element is also a 2+ ion. Meaning that when I ionize the barium, I'm not going to have to do it once. I'm going to have to do it twice. So I'm going to do it again. So barium is going to get ionized into Ba plus gas. So, and then sulfur solid, 2O2 gas, plus an electron, because remember, when that barium becomes barium plus 1, that looks plus, like it's a 4, so let me fix that. So when that barium becomes plus 1, it loses 1 electron. We have to draw that electron in, so I'll put it out here at the end. And then, so this right here, going from barium to barium plus 1, that is the first ionization energy of barium. So we're going to call that C. And we're going to label this C. Then going from barium plus 1 to barium plus 2. Plus the sulfur, plus the oxygen, plus 2 electrons. Now, because I removed the second electron. This is the ionization energy of barium, but the second one, which I have right here. We're going to call that D. So this is going to be D right here. So now we finished with the metal, right? We went all the way from the metal in its elemental form all the way up to the gaseous 2+ ion of the metal. Now we should work on the nonmetal. That's where this particular problem gets tricky, because the nonmetal is not a nonmetal, it's a polyatomic ion. It's the sulfate polyatomic ion. But look at this, and this is where you have to kind of have a good brain on you and pay attention. If we look at this, right, and actually let me highlight it. If we look at this right here, we have S solid plus 2O2 gas plus 2 electrons. Where have we seen that before? S solid plus 2O2 gas plus 2 electrons. The energy level that, or the enthalpy change that we're looking for here for this whole problem, the whole purpose of this problem, is the enthalpy change that changes this into the sulfate ion. So what are we going to do here? Am I going to then go ahead and use all of these, atomize the sulfur, do the enthalpy changes for the oxygen, for the electron affinity, do the electron affinity for sulfur? No, that's a lot of work that I don't need to do. Why? What I'm actually looking for is this sulfur plus O2 gas plus 2 electrons, turning into sulfate. So all I'm going to do is I'm going to grab all of this. I'm going to keep my barium how it is. And I'm going to turn all of this into sulfate, SO4 2 minus, gas. Because that's what I'm looking for. This energy right here, this enthalpy change, we're going to call this X. This enthalpy change X is what I'm looking for. So why am I going to break it apart into multiple steps when I just need to know what that is? And all I need to do then to figure this out is to finish this energy level diagram. I have the ions in their gaseous form. So what is the ions in their gaseous form turning into the solid ionic compound? That is the lattice energy, the whole purpose of this chapter. That is the lattice energy. So we're going to call this right here, which is exothermic, because we know lattice energy is exothermic. This one, X, could be positive, could be negative. We don't really care how we show it. But here, this is exothermic. So we know what this is. We know what this number is. We're going to call this E, the lattice energy. And we'll just call this here E. Again, we could label it delta H lattice of barium sulfate. That's a lot. That takes a while. We'll just call it E and label it on the chart, on the table. Now that I have this just became such a much easier problem. Let me actually change the color of X so we can visualize it as we do the math. We're going to make X blue, or green actually. So we'll make X green. And now we're going to do the math. Because now that we have the energy level diagram, we can do the math that goes along with it to figure out what X is. So I'm going to turn this blue. And so, again, there are two ways of doing this. You can do it whichever way you prefer. I'm going to do it the way that kind of follows the arrow. So all of these arrows, they all point up, and then they cross over and point down. This A is the arrow that is in opposite direction. So I'm going to draw my alternate path arrow that goes this way, right? And so because these all agree in direction, what am I going to do? All of these added together are going to be equal to this one. So A, which is down here, that's the one that's off by itself because it doesn't follow the pattern, is going to be equal to B plus C, so B plus C plus D plus X, so we'll change the color here, plus, and then when we go, so B plus C plus D plus X, plus on the other side here, E. But what we're looking for is X, right? So we're going to use some simple math, some simple algebra that we learned in God knows when. And we're going to say that A minus, because we want to isolate X, minus B, minus C, minus D, minus E is equal to, because we're bringing all of those over to their side, that's going to be equal to X. And that's it. Now what do? I just need to solve this problem. I need to just plug in all my numbers. What is A? A, if we look here, is negative 1473. So I'll put negative 1473 minus B, which again, we just look here, B is 180. So minus 180 minus C, which is 503, minus D, which is 965, minus E, which is negative, and that's why I keep the parentheses because of the negatives, negative 2469. And all of these together is going to be equal to X, which is what we're trying to find. Now, what we got to do is the math. We plug this in the calculator, and when we plug all of that into our calculator, the number we get is that X is equal to, so give me 1 second. X is going to be equal to negative 652, and all of this in kilojoules per mole. So kJ mole to the negative 1. And that's my answer. Negative 652 kJ moles to negative 1. See, this is a hard problem, but it's not a hard problem because the math itself is hard. I mean, sincerely, it's just subtraction and addition. It's hard because we have to figure this out. We are not directly taught to do this. This is an AO2 question. It is a critical thinking question. So because we're not directly taught to do it, we have to start with something we know, like the energy level diagram for lattice energy, and then work our way through it until we see and we have that aha moment of, oh wait, sulfur solid plus 2O2 gas plus 2 electrons is what I'm looking for when that makes sulfate. So I'm just going to grab that, make it into sulfate, and let me highlight the sulfate here. Make it into sulfate, and that is going to be what I'm looking for, that X right there. And then we just label everything else. Using labels like A, B, C instead of using things like the actual symbols is just a shortcut for testing. So let's go back to our PowerPoint. So let's go back to our PowerPoint, and if we see here the answer key, the mark scheme, you see that we got the right answer, negative 652. So what are they giving us points for? Notice that nowhere in this mark scheme, even though it's 3 points, nowhere in this mark scheme is there an energy level diagram because they don't create the diagram. It says it may be helpful to draw one, but it doesn't say you have to. So what are we getting points for? Correct 5 values used. So they're giving you points for making sure that you're using the 1473, the 180, the 503, the 965, and the 2469. Notice that when we ended up with the answer, we did not use any of these last 4 enthalpy changes. We didn't use them. We didn't have to. So they're giving you a point for understanding that and not using those 4. Only correct 5 values used. So the first point is for you using the 5 values that were correct. So it's for you using these 5 values right here. The second point, it's for not using the other 4. So if you use the first 5, you could still get a point, even if you use one of the other 4. Because the second point is only for using the correct 5 and not using anything else. And then finally, the last one, the third mark, is for having the correct answer, 652, with the correct sign, meaning negative. All right. So that's what this problem is like. That's one of the harder critical thinking problems to work through in this particular section, this particular chapter, really. It's one of the hardest problems in this chapter. So let's keep going. All right, so let's look at this now. Now that we've done the math, we gotten that out of the way, the very complex part. Let's talk about the theory behind lattice energy and what factors affect lattice energy. You have to remember that when we talk about lattice energy, we are talking about an ionic crystal. So because we're talking about an ionic crystal, we are talking about positive and negative ions that are alternating in a lattice and attracting each other magnetically. So positive ions here, we have our negative ions. And when we talk about the lattice, the lattice energy, we are talking about the creation of this lattice. And therefore, the creation of the forces of attraction between these positive and negative ions. And that any factor that affects this magnetism, this positive and negatives attracting each other, is going to affect our lattice energy. So all the factors that affect the values of lattice energy have to do with what we call charge density. Now, this is a new word that we're using, but we actually have discussed charge density a bunch throughout AICE chemistry. We just didn't call it that. Charge density is the ratio of an ion's charge to its volume. So essentially you can see it as the ion's charge divided by the ion's volume. It can be boiled down into a number, but the number itself is not what's important. What's important is the magnitude of the number. How large is it? How small is it? The higher the charge density of an ion, the more strongly it can attract the opposite ion. So charge density essentially is directly related to the magnetic attraction between the negative anion and the positive cation. Why? The higher the charge density of an ion, the stronger the attraction gets. Essentially, a higher charge density makes the ion into a stronger magnet. So the stronger that attraction is between the ions, the more energy will be released when that lattice is formed. So more exothermic lattice energy. The stronger the attraction, the more energy is released when that attraction forms, the higher the lattice energy. Again, so how do we know that? Let's look at what charge density is. When ion charge is high, then we are making the numerator in this division higher, meaning charge density will go up. So a higher charged ion charge means a higher charge density, which means a higher lattice energy. Why? Because the attraction between the ions is stronger. If we, on the other hand, decrease the ion's volume, if we make a smaller ion, or if we choose a smaller ion, then charge density will also increase. Because if we make the ion volume smaller, we're making the denominator smaller in this division. And so the charge density will also increase, and therefore the lattice energy will increase. All of this has to do with this magnetism and the stability of the lattice. The stronger these magnetic attractions, the more stable the lattice is, meaning that more energy is released when the lattice forms, and that can basically be figured out by looking at the ion charge and ion volume. Either increasing the charge or decreasing the volume, both increase the charge density, making the magnetic attraction stronger, meaning that the lattice is more stable and therefore the lattice energy is higher. And by higher, again, we mean more exothermic. So let me write that here because that's an important distinction. When I say higher, we mean more exothermic. More energy is given off. So let's look at ion size. Larger ions are going to have a larger volume. The larger the volume, the lower the ion density, like we just talked about. When we look at larger ions have their nucleus farther away from the bonding, and therefore give us a weaker attraction or weaker interaction with the opposite ion. So because the ion volume is larger, because we have larger ions, the charge density decreases, and therefore, because the large density decreases, the lattice energy is less exothermic. So we can see that here. Here we have the lattice energy, because remember, lattice energy is for a compound. Here we have the lattice energy for a different combination of group 1 cations and group 17 anions. So how do we read this? This is lithium, sodium, potassium, rubidium, and cesium. So each line represents that cation. And then each dot represents the anions paired up with. So this first dot right here, this is lithium fluoride, Li and F. This dot right here, this is lithium chloride, Li and Cl. This is lithium bromide, and this is lithium iodide. If we go down to the bottom here, the bottom line, this is the line for cesium. So this first one is cesium. Oops, that is not the right letter. So this first one is cesium fluoride. The second one is cesium chloride. This one's cesium bromide, and this one's cesium iodide. And then these middle ones are the same thing, but with sodium, potassium, and rubidium. So we can see that, as we know from AICE chemistry, as we go down group 1 or down group 17, the ions are going to get larger. Ionic size increases because of more shielding. And so as we go down on more energy levels, as we go down, the ions are getting smaller. Or sorry, bigger. Notice what happens to the lattice energies for the same anion, but the different cations. Here we have lithium fluoride, sodium fluoride, potassium fluoride, and rubidium fluoride. Let me write the ones that are missing. So here, this is sodium fluoride. So this is NaF. This is LiF. This is KF, RBF, and CSF. So notice how as that cation increases, the anion stays the same, they're all fluorine, but as the cation increases, so does the lattice energy get less exothermic. Here we have around, we'll call this negative 1050, so very exothermic. This was around negative 900, less exothermic. This was around negative 825, even less exothermic. Rubidium, which is even bigger than potassium, we have it around negative 750. And then cesium fluoride is around negative 725. So as that cation gets bigger, because the attraction between the cation and the anion gets weaker, the lattice energy gets smaller. And it's the same for every repetition of this. Here we have it with chlorine, here we have it with bromine, here we have it with iodine, but it's the same pattern. As the cation gets bigger, so does the lattice energy get less exothermic. The same is true for the anions. It's not only true of cations, but also of anions. If we look at the line for lithium, so if we look at this line right here, lithium with fluorine, which is the smallest of the group 17 elements, has the largest lattice energy. Then we go down to lithium with chlorine, which is slightly bigger, and the lattice energy decreases. If we do lithium with bromine, even smaller, and lithium with iodine, even smaller, and iodine being the largest of the group 17 elements. So this is LiF, LiCl, LiBr, and Li. So we can see that if we keep the cation the same, but we change the anions, as the anion gets larger, the lattice energy decreases. And again, that's the same reason. As the ions are larger, so the magnetism between the ions is going to be weaker, making the lattice energy less exothermic. With ion charge, remember ion charge, when we talk about charge density, is the numerator in the equation. With ion charge, as the ion charge goes up, so will the charge density, and the lattice energy will get more exothermic. As the ion charge increases, we have more magnetism. They're stronger magnets, the ions. And so the lattice gets more stable and becomes and has a higher lattice energy. So we can see this in the comparison between lithium fluoride and magnesium oxide. With lithium fluoride and magnesium oxide, the charge of the cation is higher in magnesium than it is with lithium. And the charge of the anion is also larger in magnesium than it is with magnesium oxide than it is with lithium fluoride. So here we have a compound with a +2, -2 charge, and a compound with a +1, -1 charge. Now, the sizes of the ions are fairly comparable. If we look at the sizes, we have a size of 90 nanometers for lithium, 86 nanometers for magnesium, very similar, 190 nanometers for fluorine, 126 nanometers for oxygen, again, fairly similar. So here we're kind of taking the size out of consideration because the sizes are similar. So the difference in their electronegativity, their lattice energy, are going to be solely based on the charges. And look at the difference, it's massive. The lattice energy for lithium fluoride, which has a +1 and -1 ion, is -1049. the lattice energy for magnesium oxide, where both ions have a charge of 2, plus 2 and negative 2, is negative 3,923. Why does this happen? Well, larger ion charges means larger charge density. And when we have a larger charge density, the attraction between the ions is stronger, and so the lattice energy, when the lattice forms, is more exothermic and releases more energy. All right? So that's the reason why, or the factors that affect lattice energy and how exothermic it is. The charge of the ions and the volume of the ions. Now let's kind of switch gears here and talk about ion polarization, because this is something that's brand new. We talked about decomposition reactions last year of carbonates and nitrates. But let's talk about why we have those effects, why those things happen. Well, ions are spherical normally. We picture ions as these large spheres. So if we picture, for example, the sodium ion, we normally draw it as a sphere. If we picture the chloride ion, we just picture as a larger sphere. And that is usually true. The electrons are fairly well distributed. While these ions are normally spherical, their shape can be distorted. Remember that when we talk about an ion or an atom, we're not talking about a solid thing. We're talking about an electron cloud. That electron cloud can be distorted by strong charges. We call the distortion of the electron cloud of an ion polarization. Polarization meaning that it's warped. So the distortion of an electron cloud of an anion by a neighboring cation specifically is called ion polarization. The other way wouldn't usually happen. Anions are usually much larger than cations, and because of that, usually the electron cloud of the anion is the one that gets distorted. When we look at anions can have their electron cloud distorted. So when you have two ions next to each other, the anion might have its electron cloud kind of warped and taken out of being a sphere. What dictates whether a cation can do this is called the polarizing power of the cation. And they can vary. Different cations have different polarizing powers. But again, it's all based on charge density. So the polarizing power of an ion or a cation specifically, is going to depend on its charge density. The larger the charge density, meaning the stronger a magnet the cation is, the more polarizing power it has. And the more polarizing power means it will distort or warp the electron cloud on the anion more. All right, so let's look at some examples here of this polarizing power and the ion polarization. And then we'll talk about what it leads to, why that matters. So what factors affect ion polarization? Well, these exact same factors that affect the lattice energy when it comes to the cations. So when we talk about ion polarization, we can either talk about the polarizing power of the cation. So on the cation side, we talk about the polarizing power. Or for the anion, we talk about its polarizability. How easy it is to polarize. Because we polarize the anion. So let's look at the cation first. The polarizing power of the cation is going to be dictated by its charge density. So anything that affects charge density will affect polarizing power. If the cation is small, if it has a small volume, charge density goes up, and so does polarizing power. We saw that earlier when we talked about charge density. The cation, if it has a large charge, like +2 or +3, that will also affect its polarizing power. So the higher the charge, the more polarizing power a cation has, and the smaller the ion, the more polarizing power it has. So let's take here, for example, sodium chloride, magnesium chloride, and aluminum chloride. Sodium, magnesium, and aluminum are all in period 3 and have a fairly similar size. However, sodium only has a +1 charge, magnesium has a +2 charge, and aluminum has a +3 charge. What that means is because they have roughly the same size but increasing charges, their charge density going down these cations increases. I got a little bigger on me. So the charge density is going to increase as we go from sodium to magnesium to aluminum because the charges go up. What that also means is that their polarizing power increases. Because aluminum has a +3 charge, it has more polarizing power than sodium with only a +1 charge. So what does that mean? When these are paired up with chlorine or the chloride ion, sodium will only slightly warp the electron cloud or polarize the electron cloud. Magnesium will polarize the electron cloud of chlorine a little more strongly, and aluminum will really intensely distort the electron cloud and polarize it, making it not spherical anymore. On the anion side, what affects polarizability? Polarizability is affected by anything that will affect the number of electrons or that is related to the number of electrons. Mainly two things. First and foremost is the size of the anion. The larger the anion, the more polarizable it's going to be. And the other one is the charge of the anion, because higher charge or lower charge, if we consider it to be negative, is going to mean more electrons. The more electrons there are in an anion, the more it will lend itself to being polarized, or what we say is the more polarizability it has. So if we look at fluorine, chlorine, and bromine, this is an example of that. Fluorine, chlorine, and bromine are all -1 charges because they're all halogens, but their size increases. As we go down the group of the halogens, the size of the ions increases, and so does the number of electrons. Because the size increases as we go from fluorine to chlorine to bromine, so does their polarizability. Their polarizability is also going to increase, and we can see that when we pair them up all with the same cation. These are all Al3+, exact same cation, exact same size, exact same charge. But look at what happens with fluorine, chlorine, and bromine. As we look at the fluorine is very slightly polarized by aluminum because fluorine has very few electrons, very small. Chlorine, having much more electrons, is polarized even more. And then bromine or bromide, because it's an ion, being so much larger, having so many electrons, is really highly influenced by the aluminum, getting highly polarized. So keep this in mind. Polarizability, the polarization of an anion in an ionic compound is going to depend on the polarizability of the anion, meaning the larger it is or the more highly charged it is, the more polarizable it's going to be, and the polarizing power of the cation. The higher the charge of the cation and the smaller the cation is, the more polarizing power it will have because its charge density is higher. Now that we know all of this, why does it matter? Why does it matter if the anion gets polarized? Well, with things like chlorides and bromides, that doesn't really matter. These are monoatomic anions. But when it comes to polyatomic ions, it starts to matter more. Why? Remember that in AICE chemistry, we studied the thermal stability or the thermal decomposition of group 2 carbonates. We saw that a group 2 carbonate, such as calcium carbonate, when heated, will break down into calcium oxide and carbon dioxide. Notice that this is not a regular decomposition reaction where the ions just split apart from each other. The carbonate ion in this particular reaction is actually broken apart. Now, which group 2 element we have doesn't matter, but if we look at well, doesn't matter yet. We'll talk about it in a second. If we look at the carbonate does not survive the decomposition. It gets broken apart into the carbon dioxide and the oxygen in the oxide. 1 carbon, 2 oxygens, plus the other oxygen gives us 3. Why does the carbonate break down? Well, the answer is what we just talked about. Polarizability and polarization of the cation. The thermal stability of carbonate is related to the polarization of the carbonate anion. The more polarized, the more distorted, I'm going to go back here. The more distorted an anion gets, the more unstable it becomes. As the anion gets more and more distorted, it becomes more and more unstable, meaning that it's easier to break apart. Because thermal decomposition breaks an anion apart, as we see here with the carbonate, the more polarized that anion is, the more easily it will break down into the oxide and the carbon dioxide. And so the temperature at which it decomposes starts to go down. We can see this with the thermal decomposition of those two group 2 carbonates that we have here. So if we look at magnesium carbonate, calcium carbonate, strontium carbonate, and barium carbonate, these are all group 2 carbonates, meaning the anion is always the same, so we don't look at the anion, we look at the cation. Magnesium is Mg2+. Oops, that is way too big. Magnesium is Mg2+ for a cation. Calcium is Ca2+. Strontium is Sr2+. And barium is Ba2+. Now, with the anions being the same, all carbonate, we're looking at the cations, but the cations all have the same charge. Meaning there's only one thing that affects their polarizing power, and that is size. They get bigger as we go down the group, meaning that their polarizing power goes down. So the polarizing power decreases as these ions get bigger. So what does that mean? Well, as we go down, the polarizing power of the cation decreases, so the anion becomes less polarized as we go down. A less polarized ion means that it is more stable and it takes a higher energy or higher heat temperature to break it down. So look at what happens to the decomposition temperature. As we go down, as the cations become less polarizing and the anion becomes less polarized, the temperature for which at which the group 2 element decomposes goes up. It increases. Why? Because those anions become more stable as they're less polarized. We can look at the decomposition temperature for this, or we can look at the enthalpy change of reaction. As we go down, it requires more energy, or it increases the enthalpy change of reaction for that decomposition. I mean, more energy is needed to break down those anions. And again, why? Because they're less polarized. So this is why polarization is important. It helps us understand not just the trend of thermal stability of the group 2 carbonates, the fact that they become more stable as we go down the group and require higher energies, but it helps us also understand why. Not just what the trend is, but why the trend happens. The same exact logic can be applied to the thermal stability of group 2 nitrates. Again, group 2 nitrates, just like the carbonates, are going to decompose when we're exposed to heat. Only in this scenario, the nitrate in the group 2 nitrate decomposes into oxygen, or the oxide, should I say, nitrogen dioxide, and oxygen. It breaks down into 3 different things. And again, this has to do with thermal stability. The thermal stability of the nitrates is also related to the polarization of the nitrate ion. The more polarized that anion becomes, the more polarized that nitrate ion becomes, the more easily it will be broken down into the oxide, nitrogen dioxide, and oxygen. Because of that, it can be seen in the thermal decomposition numbers, just like it was for the carbonates. We can see that because we have the same anion, we're looking at the cation. The cations, again, are group 2 cations, so as we go down, size is going to increase, meaning that polarizing power is going to decrease as we go down the group. And because the polarizing power goes down, the nitrate becomes, and this we're talking about the nitrate ion now, becomes less polarized. So the polarization decreases, and we can see that in the decomposition temperatures, which increase. So as the cation becomes smaller, bigger, it has less polarizing power, meaning the nitrate is less polarized as we move down, and we can see that affecting its decomposition temperature. The decomposition temperature goes up as the nitrates become more stable and require more energy to break down, just like we saw with the carbonates. So it's the exact same definition, the exact same theory and explanation for the nitrates that we saw in the carbonates. So just to kind of summarize it a little, what factors affect the thermal stability of both nitrates and carbonates? It's going to be factors that are related to the polarization of the anion. The carbonates and the nitrate anions are relatively large and are easily polarized by highly charged cations. So this is just saying that both the nitrate and carbonate ion, being polyatomic, are very easy to polarize. The group 2 cations increase in radius as we go down the group, which is going to affect the polarizing power. The larger the cation is, the worse it is at polarizing the anion, the lower its polarizing power. The less polarized the anion is, the more stable it becomes, and therefore the more stable the anion is, the higher the temperature it will require to decompose that carbonate or nitrate into its products of the decomposition reaction. So keep this in mind. Make sure you're able to explain this. That's why I'm showing it to you this way, because it kind of shows you all the possible points. Answering a question like this, it could be up to a 5-point question. Probably wouldn't be normally, more like a 3-point question, but these are all the levels that happen in answering that question. All right? Well, that is it for section 3 of chapter 19. I know it's a very long and very tedious section, but this is the meat and bones of this chapter. This is one of the most important sections of the chapter, particularly the energy level diagrams, the math, and understanding how to explain the effects that all of these different factors have on lattice energy and on the thermal decomposition of group 2 nitrates and carbonates. All right, I will see you all in the next video.